So this video is a part of a series on the eigenfunctions of Fourier transform. The first video we talked about introduction to Fourier transform and some symmetry properties. We talked about the next one we did more symmetry properties, talk about stuff like that. The previous one we talked about spectral decomposition of the Fourier transform, which was kind of is filled with a lot of allusions to the theory of bounded operators on Hilbert space, if you're familiar with that. It might have been a little harder to follow if you weren't as familiar with that topic. However, we'll do something now that's a little bit clearer for people without that foundation. So this is related to the ideas of symmetries using the idea of group representation. So we will make use of the following technique for forming invariant vectors for a group representation. So I'm not going to assume really that you're too familiar with group representations. And after this paragraph here, so this paragraph is the only part I'm going to use it. The rest of it will be more concrete. I just wanted to say this in case you're familiar with the idea. This is at least where I got the idea from. Anyway, so if you have a group representation, so we have a group, so there's some collection of things that you can multiply and take inverses for, stuff like that. And what you can do is you have this group representation which takes each of these things, these abstract things, and turns them into matrices in a way that kind of respects the properties of the group, the multiplication rules. And we're going to assume that the group G is finite. So this absolute value means the number of elements of the group. Then what we're going to do is define this P operator, because these right here, GL of V is invertible linear transformations on V. So in some sense, you could think of them as invertible matrices or invertible operators. So what we do is you take all the possible things, all the possible representations of G. So G is going to be filled with lots of little g elements of groups. And then pi of G is going to be the representation of that. So the thing that G is being represented as. And then what you do is you average over all of them. And we call this thing P. Now, it turns out that if you multiply by pi of H, so pi of G, group representation identity says that this is pi of HG. And a fact about groups is that if you do H and you multiply by G, that's just G. It just permutes the elements of the group. So if you do pi of H times P, then that's 1 over G, G and G, pi of H, pi of G. Now these will combine and you'll get pi of HG. And this right here, for every G and G, you're adding over a permutation of it. So I said H times G, it's just permuting all the different elements. So this right here is still the same thing as if you define G prime to be HG, G prime and G, pi of G prime, which is just P. So pi of H times P is P. Now what you can do is that you can average over the H in G. And how many average? Now this is just P, so it's P squared, P times P. And this right here, averaging a constant, there's no H's in this, so it's just P. So we get P squared is equal to P. So P is a projection. And as far as like representation theory is concerned, if you have like a nice field, then this right here is it's like an abstract idea where this P is a projection. And it's used in some of the representation theory. However, we're going to just use this small idea to apply to a very simple example. Our simple example is that the Fourier transform to the fourth power is the identity. So the simple group that we only really need is 1x, x squared, x cubed, where x to the fourth is 1. So it's a very simple group. You can think it's a cyclic group. For us, we're going to write it a little bit more generally because this kind of simple idea is actually, it generalizes a little bit. So if you have a finite cyclic group of n operators, so they're all powers of some operator whose nth power is identity. So I'm going to assume that you have identity, you have t squared, t cubed, all the way to the n minus 1. I'm going to assume that not just this is true, but the n is the smallest number where this is true. So I'm assuming that the order of this group is n. There are exactly n elements here. None of these are repeated or anything. If it's repeated, then it'll just end up being a smaller set, and there'll be repetitions, and I don't want to do that. So I'm just going to assume none of them are repeated. That's something that's actually not proven here. We didn't actually prove that f squared is not equal to 1. I mean, we know that's true. That's equal to n. But we didn't show that f cubed is not equal to the identity, which kind of follows from group theory. But we'll just assume this is true. This is true, which is not equal to the identity. So as like a fact of group theory is that we know that 1, Fourier transform, Fourier transform squared, Fourier transform cubed are all distinct. So, I mean, this definition here turns out to be this. We just average over the group divided by n. So this is what we call an orbit. So it's all the, oh, we haven't done the orbits yet. Sorry. We're just averaging over the group and dividing by n. I, t squared, t to the n. And what you can show is that if you do t times p, that's the same thing as p. Well, why is that true? Well, if you multiply t here, and you multiply t here, when you put the t in here, it takes this and turns into this. You multiply by t, it turns it into this, etc., etc. This, if you multiply by t, it turns it into this. So it cyclically permutes all of the elements of the group. That was exactly what we had up here. It permutes the elements of the group. So TP is P. And what can you get from this? I mean, you can also check that if TP is P, that means T squared P is also P. And T cubed P, and et cetera, et cetera. And then what you can do is you can average all of these, and then you get P squared is P. So we get a projection, just like we had up here. However, we're focused specifically on the fact that this is true. So let's take a vector in the vector space and apply P to it. So PV, you apply T on both sides, it doesn't do anything. So it tells us that PV is an eigenvector of T with eigenvalue 1, or it's 0. So this is a nice way to cook up eigenvectors with eigenvalue 1 for T. What you can do is you can use the same kind of trick to cook up other eigenvectors with eigenvectors with different eigenvalues by just changing the operator T. So let's see how to do that. Because this trick only really gave us eigenvectors eigenvalue 1. So how can we turn this problem into an eigenvector problem with eigenvalue 1? So if we have lambda to the n is 1, so just non-zero, what we can do is we can divide by lambda. Lambda inverse t is, times v is v. So now, if this is a new operator, say SV is v, this becomes a new problem with eigenvalue 1. Just like just kind of problem we're looking at. So we're going to apply this trick, so to speak, to this operator. And then if I call this s, then I still need s to the n to be the identity. But that's true, because if I take lambda, which is an nth root of unity, nth power is 1. And if I raise it to the nth power, the n comes in, I get lambda to the negative n, c to the n. This gives me identity, this gives me 1, so it's just this. And this is the problem that I'm trying to solve, which is the same thing as TV is lambda v. So it'll give me a lambda eigenvector or a 0 function. So now, just using all that, for each lambda that's nth root here, I can define this p. So I'm going to call that p lambda. And this is the formula that we had. We had summing over the powers of this operator s here, and then averaging them. And we see that p lambda is a projection. We know that p lambda, the range of p lambda belongs to the lambda eigenspace of t. However, what we're going to say is we're actually going to show is that p lambda projects onto the lambda eigenspace of t. So what it means is that there's an equality in the opposite direction. So we showed one, we're going to show the other. So in order to show this one, which is the one we have to show, we have to show that every eigenvector, if I apply p lambda to it, the same lambda, it should still remain it shouldn't change the vector. So if I have a vector that's an eigenvector, or just in the eigenspace, so it can be 0 or whatever, just satisfies this equation, then if I apply p to it, it shouldn't change the vector. So let's just do that. P lambda v is, well, this right here is p lambda times v. Now let's focus on this part, because tv is lambda v. If you do t k times, you're going to get lambda k times. So this right here becomes lambda to the kv. The rest of this obviously remains the same. Now the lambda k, negative k and lambda k, they cancel. So you're averaging the same thing, the vector. So you just get the vector. The key idea is that this negative lambda here is supposed to cancel out the eigenvalues that you get from this t to the k. So p lambda v is just v. And so what we showed is that p lambda projects onto the lambda eigenspace. So it is a projection onto the eigenspace of t. Now, in order to get some nice structure, like maybe you want p lambda star to be p lambda, which is that it's an orthogonal projection. And maybe you want the projections with different lambdas to be orthogonal to each other. You need that t is a normal operator. However, we're not assuming that at that point. It's true for the Fourier transform, but we're just not assuming that. We're just talking about eigenspaces. So now we have this thing. This is a fact about it. It's called eigendecomposition. This right here is going to give us our spectral decomposition. We're going to be able to take every vector and write it as a linear combination of the eigenvectors of t. So let's see why this formula is true. So if we take this right here and we define what p lambda is, this is what p lambda is with the 1 over n. Maybe it's a little clearer actually if you write out what this is for actually what we're doing. So we have these different things here, different lambdas, different t to the k's, and we're going to be adding over the lambdas. So in some sense, we want the lambdas to cause a whole bunch of cancellation, so we're just left with an identity. So that's the idea. So we have this here. Let's interchange the sum. It's lambda to the n. This thing only depends on lambdas. This thing is the only thing that has lambdas, so we can just put this thing in here. So this thing has the k. There is a k here, and this is the only thing that has lambdas. So now we need to find out what this thing is, this little sum here. So the set lambda, where lambda to the n equals 1, these are all the things that have nth power equals 1, the nth roots of unity. These are the same thing as the nth powers of this thing. This is zeta is e to the 2 pi I over n. This is the principal nth root of unity. And the n powers of it are all the things that have nth power 1. So I could rewrite this sum in terms of zeta, which is that sum over lambda to the n equals 1, lambda k, is this thing, because lambda is this. And instead of lambda, different lambdas, I'm going to be summing from m equals 0 to n minus 1. And then I'm summing over m, so I'm going to write it as a geometric series in terms of m. So I'm summing a geometric series. This is something. This is going to be omega to the m, and I'm summing it. Now, it's a fact that if omega is the power of k, zeta to the k, where zeta is this nth root of unity. Now, if omega, if it satisfies this equation here, which is true, because zeta to the 1 is zeta to the n is 1, if I raise zeta to the kth power and I raise it to the nth power, it's still going to be 1. So it satisfies this. Now, From this, either omega is 1 or the sum here is 0. If omega is 1, the sum here is obviously n, because I'm adding the same thing from 0 to n minus 1, so n times. But otherwise, this sum is by definition this. That's what the sum is. And then using the geometric formula, it's 1 minus omega at the n over 1 minus omega. Now, if omega is not equal to 1, then this formula is actually true. So if this is non-zero, and then you get 1 minus 1, which is 0. So this sum is equal to 0, or it's equal to n when omega is 1. So let's go back up. This sum of projections is 1 over n. This right here, I'm just copying this right here. That's what this is. Sum over projections is 1 over n, this sum, and I have this thing isolated, which thing I cared about. This thing is the sum of this thing, which is the sum m equals 0, n minus 1, omega to the m. And omega is equal to 1 exactly when k is equal to 0. So what I get is that this thing, when k equals 0, it gives me n, because you're adding 1 over and over again. But if k is not 0, then just give me 0. So when I do the sum here, I have a whole bunch of sums of different k's, but the only k equals 0 matters. So I have 1 over n, this thing matters, this thing cancels. Only when k is 0. K equals 0 tells me this is t to the 0, which is the identity. So n is identity. So that tells me that this thing is the identity. This shows this. This implies the spectral decomposition of t. So if I take t and I multiply on both sides, well, this thing is going to give me t. That's that. Tp lambda. Tp lambda is lambda p lambda. Why is that true? Well, remember, we showed that Tp1 was P1. That's kind of what we constructed. And then P lambda was constructed for this operator S is lambda inverse T. And then S P lambda is P lambda, which means that lambda inverse TP lambda is P lambda. So TP lambda is P lambda times lambda. Also, it just follows from the fact that P lambda projects onto the eigenspace. Anyway, so T is the sum of lambda P lambda, because T times P lambda, it just gets a lambda here. So this is the spectral decomposition of T. If T is normal, then these things will be orthogonal projections, and the ranges of these orthogonal projections will be orthogonal. So this is going to be a very nice decomposition. Also, from this, the decomposition of P lambda is the identity, you can apply that to any single vector v. What you get is that v, which is this thing, is the sum of P lambda v. So if you define v lambda to be P lambda v, this right here is going to be an eigenvector, or either 0. And if you're summing over them, you get just v as being broken up into eigenvectors. And again, if T is normal, then P lambda are orthogonal projections with orthogonal ranges, and the V lambda are orthogonal. Okay, so all of that was very abstract. We did this to explore the Fourier transform to the fourth power with identity. However, there are some kind of natural examples that you've likely seen before. So let's consider this example, which is C. From C to C, it's going to be an R-linear map, which means that it respects real numbers as far as linear. It's linear. However, we are going to define it to be a complex conjugation. So this right here is going to be R-linear, but it's not linear as a map of C vector spaces, because it doesn't respect the complex conjugation. I mean, it doesn't respect complex numbers very much. It doesn't respect the I. You also know that C squared is identity, because if you do it twice, it undoes itself. So if you had Z is A plus IB, this is actually a thing that you're very familiar with, is that Z can be broken up as A plus IB, where A and B are real. Well, what does that actually mean? So A is real means that it is its own complex conjugation. That's what a real number is. B is its own complex conjugation. Now, this IB thing here says that if you take conjugation of IB, that's negative IB. Now, before I go on, I want to actually go back up to this example here and explain what this P is doing in this example. So here, or no, actually, I want to do it here. If you do P1, we said that was 1 over n identity plus t squared plus n minus 1. So if I have V1, which is the eigenvector with eigenvalue 1, that's just 1 over ti plus t squared plus tn minus 1, all applied to V. So here I have a t, I have a v, I have a tv, I have a t squared v, I have a t cubed v, all the way to tn minus 1v. This right here is what we call an orbit. It's all the possible things you can get by applying t to it. It's the representation theory idea. So V1 is the average of the orbit of V under T. So I have these different things that I can get by applying T, and then I just average all of them. And this right here gives me an eigenvector with eigenvalue 1. Now, if I want eigenvector with eigenvalue lambda, then I need to average the orbit of a different operator. It's not T anymore, it's that S. But it's the same idea. I'm still averaging an orbit. Negative n minus 1, Tn minus 1, V. I'm still averaging the orbit for the different eigenvalues. So in this example here that we had, C squared is the identity, which means that C, the eigenvalues, are plus or minus 1. These are the only values of lambda I can consider plus or minus 1. For 1, I'm going to be averaging over the orbit of C. So if I have A, I'm averaging over the orbit of C. So I'm taking Z by itself, and I'm adding its conjugate, and I'm averaging them. And that right there is going to give me something that is an eigenvector with eigenvalue 1 for C. So it's going to be a real number. That's this. This B has always this weird formula with this I down here. The reason why it has this weird formula with the I down here is because I should actually be up here with the BI. So BI is Z minus Z bar over 2. And because the eigenvalue is negative 1, you're actually averaging over the orbit of minus C, which this is the identity applied to Z, and this is minus C applied to Z. And you're averaging those. And that gives you BI. And BI has eigenvector, is an eigenvector with eigenvalue 1 for minus C, which is the same thing as minus 1 for C. So when you think about this, it's actually a pretty neat idea. Basically, you have C of Z, this is conjugation, C squared is the identity, and you're able to break it up. You're able to break any complex number up into eigenvectors as far as C is concerned. It's a linear, it's an R linear map. And C you can think of as R2 basically. It's a two-dimensional vector space. So you have two different eigenvectors, and this is the eigenvector with eigenvalue 1, and this is the eigenvector with eigenvalue negative 1. And then this kind of decomposition is actually the exact same thing that you've probably seen in the Euler formula. Now, I want to do a different example, but it's kind of the same example, which is suppose you have n by n matrices, and you define the star operation. And this is called, it's a convolution, and in general, that's what it is. It's a, for the specific example that we have for matrices, is called the adjoint. It's a conjugate transpose. So you have a matrix A, and you do the conjugation, and then you make a transpose. The key fact about it is that if you do both, first thing is that it's R linear, because transpose is linear, conjugate is kind of like that example we had earlier. It's R linear, and it satisfies this. Star is C. So it undoes itself. It has order 2. So if you have any matrix, you can do the exact same decomposition you have up here using averaging over the orbits. You have average over the orbit of star, you get A is this. You have B and or actually IB, I guess. You have IB is averaging over the orbit of minus star. And you could have this decomposition. C is going to be written as the eigenvector with eigenvalue 1 for star, and then -1 for star. And then A is usually called the real part of C, and B is called the imaginary part of C. And there are a lot of analogies here for real and complex numbers, and it's a very important construction for all different kinds of things. However, you don't usually think of this star as a linear operator and A and B as eigenvectors for it. However, it is very useful to think of this as a linear operator for all different kinds of reasons. But I just wanted to illuminate that there was some structure here that comes up due to these symmetries. And we're going to do another one. This one's a little bit more relevant to functions. You have a function that's in L2. You have n squared as the identity. That's the same thing as saying, we already had this example. N is the function that takes f and it replaces its argument with negative x. Now this function is n squared as the identity. So what you can do is you can take any function and using the same stuff we had done before, you can break f in terms of eigenvector with eigenvalue 1 and eigenvalue -1. So nf plus is f plus, and f plus, and n of f minus is negative f minus. So f plus, well, what is f plus? F plus is taken, how do you get f plus? You get it by averaging over the orbit of n. So you do f plus nf over 2. And that is just f of x plus f of negative x over 2. F minus is what you do is you average over the orbit of negative n. Because n squared is 1, so the eigenvalues are plus or minus 1. So we have f minus is f minus nf over 2. And that's just f minus f of negative x over 2. And this right here is going to give me an even part of f in some sense, and then an odd part. So you took any function, I broke it up into even and odd. Using the symmetry. The symmetry is what really got me to be able to break it up like that. Now what we're going to do is apply this for the Fourier transform. The Fourier transform satisfies this. So we have the eigenvalues plus or minus 1, plus or minus I. Now we're going to have a decomposition of f is f1, f negative 1, fi, f negative I. And these are all going to be orthogonal functions because f is normal. And we're going to have all these decompositions for f1, f negative 1, and such. So here we have f1, which is f, and we're going to average over the orbit of Fourier transform. So we have f, we add its Fourier transform, we add the Fourier transform of that, we add the Fourier transform of that, and then they're going to repeat. So we have 4 different things, and that's what we have. Now, using the fact that if you do the Fourier transform twice, you get n, which is going to give you negative x. We have f here, Fourier transform. Second function is going to be f of negative x. Third is going to be Fourier transform with the negative x. So this is f1. This is going to be an even function. Sorry, I don't want to get to even yet. This right here is a Fourier this is a function that is an eigenfunction for the Fourier transform with eigenvalue 1. That's the one here. You could do it with -1, and so what you do is you average over this thing, but you have to put negative signs. You have a negative sign here, and we have a negative sign here. It's going to be -1 squared. We get negative here and negative here. We're going to have an I, so it's going to be, remember, it's going to be lambda to the negative k. So we have negative lambda, and then negative lambda squared, which is -1, negative lambda cubed, which is negative lambda, so this is going to be negative I, so negative I to the k, negative of negative I to the k, excuse me, so it's I to the k. So we get I, -1, negative I. And from this decomposition, what you notice is that we have f here, and we have f negative over 4. However, you can kind of see that this is kind of this one we had up here, this f plus here. F of x plus f of negative x over 2. And the same thing here. This right here is this thing plus this thing. This is the f, the positive part of, the positive decomposition part of the function. So we have f plus minus Fourier transform of f over 2 plus. That's f1. f negative 1 has this again, but now there's a minus on both of these as opposed to the plus. So f minus 1 is this, but there's minus here instead of plus. For this one, fi, you have f of x minus f of negative x. So that's kind of like f minus. And then we have minus I plus I. So it's going to be minus I Fourier transform of f plus. I think, yeah, so that's what I have here. Or I apologize. So it's not plus, it's minus. It's minus because these have different signs. And then this one, because these have different signs as well, but there's a plus here, so this is going to be the plus one. So the point is we took f1, f minus, fi, f minus I, and wrote it in terms of the positive and negative parts of f and its Fourier transform. So what do we get from this? We get that if f is positive, what we get is that if f is even, then what happens? If f is even, then f plus is just f. The Fourier transform is even, so f plus of the Fourier transform is just the Fourier transform. So f1 is the average of f and its Fourier transform. That's the example that we had earlier in the introduction here, that we had functions like these Gaussians, and we were taking these two and we're adding them, and we got Fourier transforms. Now, if a function is even, then what happens here? Well, f plus is still f. Fourier transform f is still f plus. So f minus 1 is f minus f Fourier transform over 2. So if I have an even function, I could break it up into its function with eigenvalue 1 and with eigenvalue negative 1, based off these two constructions that we had done already earlier. Now, what happens if we look at these ones? Well, f is even, and f minus is going to be 0 because it's even. There is no odd part of it if it's even. The same thing with this Fourier transform. The same thing with these two. So fi and f negative I is 0, are 0. So if f is odd, the exact thing opposite happens. If odd, these parts are all 0, so they all vanish. So f1 and f negative 1 is 0. But f negative 1 and Fourier transform negative 1, now these are going to be well defined. They're going to just be f and f transpose. I mean f Fourier transform. So we're going to have Fourier transform, f here, minus I Fourier transform over 2. And then we have f plus I Fourier transform over 2. And this is going to be we have an odd function. We break it up into a function with eigenvalue I and with eigenvalue negative I. This kind of nice decomposition here is actually very interesting, how evens break up in this way and odds break up in that way. And it comes from the fact that f squared is n. So in a certain sense, f is a square root of n, is a single square root. There might be other square roots. I mean, in fact, there are. But Fourier transform is a square root of n. So what we would expect is certain things with the eigenvalues. So we have eigenvalues plus or minus f. I mean, if we have plus or minus 1 for eigenvalue of a square root, well, n is going to be f squared. So when I square it, the plus or minus goes away, and I get nf is f. And that's the same thing as being even. So plus or minus eigenvalue gives me an even function. If I have plus or minus I for the eigenvalues, then when I square it, I get negative 1. So it's the same thing as being odd. And now, if suppose you wanted to go backwards in this diagram, these right here are back and forth because these are identities. Here, if we have nf is f, that means f is even. What we showed is that it breaks up in terms of eigenfunction with eigenvalue 1 and with eigenvalue negative 1. So if you're here, you can go back here, but instead of having identity here, f becomes a sum of f plus f minus. f1 and f negative 1. So in a certain sense, f is a superposition of solutions to this. Same thing here. If you have this kind of eigenvalue here, you go back here, but f now needs to be a sum of one solution to this with a positive and the sum of another one with a negative sign. So there's a certain superposition. Yeah, so that is the decomposition that we had here. So we took even and odd function. We showed that there was a deep relationship between how to break up a function in terms of its eigenvectors of the Fourier transform and whether the function was even and odd. So we kind of have like a filtering. So we first go to even and odd functions. We break a function up into even and odd. And then from each even and odd, we break it up into plus or minus 1 eigenvalue or plus or minus I eigenvalue. And you can do that using this kind of thing here. So in principle, if you just take any function that you have, it's kind of function like this, something you know how to take its Fourier transform up. This is an even function. Then what you can do is you can do this kind of decomposition here and get eigenvectors with eigenvalue 1 and negative 1. And then you can take other functions that you know that are even or odd, something like this is an odd function. And what you can do is you can break this up in terms of its eigenvector with the eigenvalue I and negative I, using exactly this. And the way to calculate the Fourier transform would be a little messier, and we'll talk about that a little bit later in this series. So just for summary, we talked about some of the symmetries. We talked about how to find eigenvalues for different eigenvalues for some kind of cyclic group of operators. And then we were able to give a spectral decomposition from it. And we applied it to some common examples. We applied it to even and odd functions, and then we extended it to the Fourier transform. But the same idea applied to all these different examples, which shows that this kind of symmetrization idea is a very deep idea that comes up in all these different ways in analysis and all other kinds of ways too. There's another note here, which we'll talk about later in terms of the polarization identity. It's another example of where these symmetrizations come up, and it's an interesting idea to think about, and it's a good thing to know about. So I hope this was helpful, and we'll continue the series in another video.